third Maxwell's equation is due to Gauss law. The way in which we speak about this is this. Third Maxwell's equation in integral form is over a region, integral over a closed surface. It is here d bar dot ds bar only. Gauss law is for displacement flux density d bar is equal to q. Please remember equal to q. Q is what? Net charge enclosed by the closed surface, integral form. Next, point form. This is what is important for us. For the sake of development of waves, talking about solutions, formulation of wave equations, we take at any point the way in which the field quantities are related is wave equation. Point form is what? Divergence. Point form is del bar dot d bar at any point is equal to volume charge density at any point. At any point is in the field. At any point in the field. Point form is also called as, this is also called as what? Differential form. I think you agree this. This we are supposed to remember for the sake of the next level of subject. This del bar dot d bar is equal to rho v. Along with the expression for electric field intensity as a function of gradient of potential. Gives me the Poisson's equation, which we use to determine the field in the junction region of a PN junction. I was telling about this. Poisson's equation is not given in the fields because they removed electrostatics here. They added Poisson's equations in semiconductor physics because that is required for us. Please check it. At any point in the field, integral form is general Gauss law statement. At any, this is also called as Gauss law in point form. Gauss law at any point. This we know very well. I'm ready to explain your doubts, beyond which today I'll speak about a few good applications of Gauss law which are useful to us. Anyway, later on I will be using them to determine other field quantities, but here itself let us know it, so that there I will just straight away put this formula and say because of it is this. Please check once. I think guys, the Gauss divergence theorem is done. Gauss law I told. What is continuity and discontinuity I told. If it is continuous at a particular point, I can determine the rho v. That's what I told. divergence of a vector field, I told. General expression I gave in different coordinate systems. Then Gauss divergence theorem we stated. Ultimately, I spoke about third Maxwell's equation because they 1, 2, 3, 4. He numbered it as a mathematician. This is what we study in Maxwell's equation. First equation that I study is Gauss law. That is third Maxwell's equation according to Maxwell's numbering. But we have to remember this as third Maxwell's equation only. Because there are examinations I saw where they say third Maxwell's equation is due to which law? It's basically these are being studied as the applications of Gauss law. But in my view, I told you, right, every charged surface, every charged object, charged with q coulombs, if it is positive charge, emits q coulombs of flux. I told all those things. And if it is there on the surface, these flux lines will come out of the surface in the direction perpendicular to the surface, that because of which we say that the surface charge creates normal flux. Using the same concept, I showed, I think yesterday, that rho L by 2 pi epsilon r can be derived for an infinite filamentary line charge. And rho s by 2 epsilon as the field intensity is derived for infinite surface charge of charge density rho s. Those two are the cases where we can derive the expression for the field intensity. The cases that we are going to see now are the cases where we cannot derive the expression for field intensity, starting from Coulomb's law and integration. But using Gauss law indirectly, or those two statements, we can determine the electric field intensity. Listen, first application. This is what I use later on to determine the capacitance of a parallel plate capacitor. Suppose I have two plates of area A exactly parallel to one another and separated by a distance d. One having positive charge of q coulombs on its surface, practically possible. One having equal amount of negative charge on the other plate. I want you to understand it here because even if I go to PN junction, I am going to use this concept only. People derive the expression for field and are using Poisson's equations, all those things. But we will be in a position to, because of this knowledge, straight away talk about the field distribution in the junction. When I look at the front view of it, these two are just lines. Positive charge on the surface, inner surface, definitely negative charge on the inner surface. This is the parallel plate capacitor charged. These two conductors will have the same amount of charge. Why? It is in the system. When I say that the conductor is positively charged, fixed number of electrons are removed from it. In a circuit, it is not possible for us to remove electrons from a conductor throughout into the space. No, they will go into the other conductor because total charge of any overall system should be equal to 0. That goes, those electrons will go onto the other plate because they are oppositely charged. They polarize onto the inner surface. Suppose A is the area of the plates. Q plus Q and minus Q are the charges on the plate. Immediately I will know there will be electric field in between the plates. And that electric field lines are flux lines. They start at positive charge in the direction perpendicular to, they also terminate on the negative charge in the direction perpendicular to the surface. See the most wonderful point about it here. The flux lines are a set of parallel lines in this volume. How many flux lines will go from one plate to the other plate inside the dielectric medium? Q number of flux lines, because Q charge created Q flux lines. Those Q flux lines got terminated on negative charge Q. At any point, if I want to determine the electric field intensity, I want to consider a plane perpendicular to these lines. Calculate the flux density. What is flux density? D to the right, Q by A. Correct? Any doubt? D is equal to Q by A. Please see this. And what is E? Here, if it is said this is plus AX, D bar is equal to AX. E bar is equal to Q by A epsilon AX. One point worth speaking about here is that if I have two charged plates of area A, parallel plates of area A, charged with Q coulombs, the electric field intensity in the region between these two plates is from positive plate to negative plate direction, and it is independent of the distance between the plates. Distance is not there in the formula, I can see. Very important point here is that it is independent of the distance between the plates. Ultimately, we are going to determine the capacitance of this capacitor. Potential difference, we are going to determine. That potential difference depends upon D. But the electric field intensity in the dielectric between the plates of a parallel plate capacitor is a function of charge and area only. It is independent of the medium, we know. Sorry, flux density is charge by area. Electric field intensity depends upon charge, area, and the permittivity of the medium. It is independent of the distance between them. Next. Listen carefully. Wonderful application of it. Suppose I have a spherical metallic sphere of radius A. Charged with Q coulombs of charge. If it is charged with Q coulombs of charge, this charge will be uniformly distributed on the spherical surface. Listen, if you are not happy, I will explain it in different ways. Don't worry. This charge resides on the outer surface. Why not on the inner surface? Why not on the inner surface? Somebody can, because we discussed it, I'm talking about it.
Flux lines intersect at the origin.
If they are there in the intersect inner surface, they go towards the center because there should be radial lines. They intersect at the center because they cannot intersect. Intersect means what? There are two fields. At a point, there cannot be two fields. There can be only one unique field. It comes onto the surface. Because they repel each other, they try to be there at the maximum possible distance. One more point about it. Because, carefully say this, if there is some field here at this point, the field at any point on the circle passing through this point and concentric to this circle that I see in the figure, field should be same. Field should be same at any point. Because this is sphere, the source is sphere. At any point on the concentric sphere passing through the point of interest, the field should be same. Why? Because the way in which the sphere will be visible to this point is same irrespective of from where you want to see. You see, the way in which the charge is distributed is same from whichever the point on the outer spherical surface you look at the sphere. The position of the source, distribution of the source appears to be same. Is same, because of which there should be same field everywhere. To determine, listen carefully, electric field intensity at the point of interest. Let this be the point. I need to find out the flux density. Since the flux lines will go into the space with spherical symmetry, I told you how to calculate the flux density at any point when the flux lines are given. You have to draw a surface which is everywhere perpendicular to the flux lines. Normal flux density only we talk about. Instead, at this point, I can consider a small spherical surface, whether it is because it is uniformly distributed over the entire sphere also. What is the flux density at any point on the line, on the sphere? At this point, and at any point on the outer sphere, outer imaginary sphere passing to the point of interest, as long as that sphere is concentric to the inner sphere, flux density d bar is equal to what? Q by 4 pi r squared here. This is of radius a. For r greater than or equal to a. You agree with this? What is it for r less than a? Because there are no flux lines, there is no charge on the inner surface for r less than a. Check it. No, this is why actually magicians know they stand inside a metallic sphere and then that arcing will be taking place toward the sphere and all. Nothing will happen to him because whatever happens, no field will be there inside. Nothing will happen to the fellow. Right? Electric field intensity is what? E bar is equal to Q by 4 pi epsilon r squared for r greater than or equal to a, 0 for r less than a. Carefully see this. This is good actually. One more statement for us. I want you to concentrate. Because there is one more example where I can say that the normal component of the flux density at any boundary is discontinuous by the amount equal to surface charge density, I told. Here, if I start moving from center towards infinity, I think you agree with me that until if this is E bar, E or D, sorry, D only. Later on E. Radial D. How will it vary? 0 since A till A. At greater than or equal to A, it is this. At A, it is Q by 4 pi A squared. Is it continuous? Is flux density continuous? At A minus it is 0. At distance A plus, I have gone out of the sphere. It is Q by 4 pi A squared. The sudden change is the amount of discontinuity. What is the amount of discontinuity? How much is the change? How much is the change? From 0 to Q by 4 pi A squared, sudden change. What is Q by 4 pi A squared? Q is the total charge distributed on the sphere of radius A. 4 pi A squared is its area. Charge per unit area is Q by 4 pi A squared. Here also, earlier it was rho s by 2 negative to rho s by 2 positive. Discontinuity is rho s. Here 0 to Q by 4 pi A squared. At that point on the boundary, it need not be infinite boundary. It can be finite boundary also, is what we should know. Before A, it is 0. Just after A, it is Q by 4 pi A squared. It is discontinuous at A, where surface charge is there, by the amount equal to Q by 4 pi A squared. That Q by 4 pi A squared is the surface charge density. Is it fine? Q number of flux lines will be emitted with spherical in the direction perpendicular. They are all radial lines, right? If I have a sphere and there are so many radial lines going out of the sphere, they pass through any concentric sphere radially only, correct? Any other sphere of greater radius, if you consider, if it is concentric to the initial sphere, they will also be radial lines at that point. Everywhere radial, because of which I say a radial only is the direction, AR. One more application. Some more I will talk about when we talk about capacitances and all. Spherical surface of radius A. Spherical surface of radius B. Two surfaces. Two concentric surfaces. Spherical surfaces of radii A and B. System of conductors. Let there be positive charge on this. It goes on to the outer surface of the inner sphere. equal amount of negative charges distributed on the inner surface of the outer sphere. Let us suppose these two conductors are there in a system where charge Q on both conductors is same. Definitely field inside is 0. Field outside also is 0. Why? Total charge, spherical distribution, total charge enclosed by any closed surface of radius greater than b is what? Equal amounts of positive and negative charges, because of which it is 0. Let's check. Inside, Q flux lines will be going out radially, correct? I want to determine the electric field intensity at any R. I will consider a surface which is everywhere perpendicular to the flux lines, such that the field is everywhere same. On that R, flux density is Q by 4 pi R squared d bar. For A outer radius B, A less than or equal to R less than B, less than or equal to B also you can put. Zero elsewhere. And the electric field intensity E bar is equal to Q by 4 pi epsilon R squared AR. For A less than or equal to R less than or equal to B, 0 elsewhere. Wherever D is there, E will be there. Please check it. You are supposed to remember all these things properly.